Is we're going to continue where we left off, and that last time we talked about Fiona and we talked about getting enough signal, and a lot of fluorophores have a limited photostability. They tend to die after a while, and that's particularly true of fluorescent proteins. And so one way that you can do it is you can just add a bunch of fluorescent proteins. And as long as they are organized such that, they move all together, it works out just fine. So if you target an organelle or something like that, the thing looks no problem. That the fact that there are maybe extended, certainly it can be extended out to like a micron, but as long as that thing moves as a unit, you can actually locate it to within a few nanometers. Okay, and we'll get to perhaps another case where you're actually looking at something that's not even fluorescent. And there's a little bit of trick to getting the signal. But for now, we'll talk about Fiona, and then we'll essentially immediately talk about Storm and Palm in terms of the resolution. Okay, so you've seen this many times. Has the width which is 250 nanometers. The center you can locate much more accurately than that. If this thing moves, as in the fluorophore is connected to on a molecular motor or something, you can watch it move. Okay, so what properties of dyes do you need for Fiona, that is, for super accuracy localization? So what we actually covered this last time, but this is just to get your mind going again. So what is it about the properties of the dyes that it is good? Photostability. Yeah, photostability. That's essentially what there is. Okay, now, so what properties of dyes do you need for Storm or Palm, that is, for super resolution localization? And for that matter, what is super resolution as opposed to super accuracy? So what properties of the dye do you need for Storm or Palm?
For super resolution, would it have to be high intensity?
High intensity. Why do you need high intensity?
No. Not necessarily. I guess dyes that can be excited with low intensity. Okay.
Why? Whatever you say, I'm going to say.
Turning on the dyes. So we would like to control how many dyes per intensity pulse.
Right. Okay. You're.
And also because we want to look at single dyes, that's why I thought they should have high intensity. Enough intensity that we can distinguish them from the background.
Right. Okay. That's good. The dyes need to put out enough photons for you to be able to see it in whatever time you're trying to look at. In fact, that's also true with Fiona, because in order to localize it, it basically looks like the width is just 250 250 nanometers divided by the square root of n. So if you only get a few n's during the time at which you'd like to locate it, you know, Fiona is going to look like crap. Okay? So you definitely need enough, not only photostability, but that it puts it out at a fast enough rate. And in general, almost all fluorophores will put it out at a fast enough rate. Why is that? A fluorophore, what limits it in terms of how fast you can get out your fluorophores? Your photons. So you have a single molecule that's there, and you want to image it. And how well you can image it will be depending on the number of photons that you get out within 1 second, let's say, or within a tenth of a second, or within 10 seconds, or something like that. So what determines how fast the molecules will come out of the fluorophore?
Well, that's why we use the agents to prevent going through the microscope.
Yes, but the quantum efficiency.
If you have a larger population at the excited state, then chances that, well, so on some level that more fluorophores will be turned on, right?
Yeah, but we're not talking about in ensemble. We're talking about a single dye.
By chance, right? You have a higher chance of being in an excited state than higher chance of fluorophore.
Right. So the fluorophore should absorb, have a large enough extinction, and then once it's up there, you want it to re-emit rather than just come down. So that's in the quantum dot. How long does that take? What's that? Nanoseconds. So in general, if a dye has, let's say, a nanosecond lifetime, that means it can put out 1 over a nanosecond, or 1 billion photons per second. It won't last in general, but it can put out that many. Although after 100,000 or 1 million, it put out that amount of photons, it'll die. Okay? So essentially, any molecule will put them out fast enough. What ultimately it's limited by its photostability. Okay, and now what properties of the dye do you need for storm or palm? Good. We're very, very close. Yes.
So, like the ability to just rest for a while, not photobleach very quickly, longish. I don't know what the antonym of photobleaching is. Photostability.
Yeah. So you want it to be very photostable or not photostable?
Very, I guess, photostable, but somebody else said it before.
Yeah. So what do we know about super resolution? What is it?
You can distinguish things that are really close together.
Okay, so if you have 2 molecules, and they're coming together like this, and by really close, what do you mean by really close? Lambda over 2. Ordinarily, they would both be emitting, and it would look like a mess, right? So at least with storm and palm, the way you're going to get like Fiona type resolution, how are you going to do it?
So you're exciting different fluorophores at different times?
Exactly. Exactly. You're exciting different fluorophores at different times. But wait. But with Storm, you have an identical fluorophore right next to it. So how are you exciting different fluorophores at different times?
So you want your fluorophores to be more prone to photoblinking, I guess?
Photo blinking, yes. That's the important point, is that yes, you want them to be photostable, but you want them to be to blink, or to be switchable. So if you have two of them here, and they're very close, you're going to excite both of them if you excite them hard, but if you turn down your intensity enough, one of them only will be excited. In fact, the way to do it very commonly is you go towards the UV, let's say 400 nanometer light, and you give just a little bit. Then, in fact, the molecules that you use are off, though they become on with a little bit of 400 nanometer light. But they only become on, that is, only one of them tends to be on. So you shine 400 nanometer light on it, it goes on, then you shine some visible light, you get that to fluoresce, and then when it's finished fluorescing, namely, generally it photobleaches, then in fact that one's off, and then you shine 400 nanometer light on it again, and this one comes on. Okay?
So photoblinking in terms of the state of the dye, is that like some kind of triplet state? The electron cannot get...
It depends. In fact, if we have the time, I'll go over it. But you can have, like GFP, green fluorescent protein, but if you make a mutant of it, it doesn't emit at all unless you shine 400 nanometer light on it. So that's one type. However, either have done or will do, we'll go over this. Some dyes, you can shine a strong light at it, and what happens, it will go in some other state that is not photobleached, that is not permanently photobleached, but goes to a dark state. Who knows what it is? And then you actually can shine a little bit of light, and then it'll come back. Okay, yeah?
We have a question. So usually the fluorophore, when it's turned on, there's only one electron being excited at a time, right?
Yeah, one electron, yes.
Okay. So that's why we got a single loop or a complex weird
Okay, you can ask the question again. So the important point is they should be reasonably photostable such that when it's on, you're actually getting a reasonable number of photons to determine its location. And then you better be able to turn it off and really turn the other guy on. Do you have a question? Yeah. Okay, great.
So is the triplet state or the state at which it's photobleached, or not? It's just not able to.
It may have to do with the triplet state, although it frequently doesn't. you treat it sort of like magic. In the sense of a GFP that is not in a state that will fluoresce. And then you can make it by shining 400 nanometer light. That is actually understood, and that is not a triplet state. And then you knock that other state into the fluorescing state. And in terms of other molecules that, you shine this strong light on it and it goes into some sort of dark state, which is then sort of, you can slowly recover. The truth is, I don't think it's known. The photostability, photobleaching is largely a black box. Yeah, it really is. I decided that I was going to look into it, and I spent, I don't know, over a year on it, and I got slapped around. Okay, so what you have with super resolution, we're just going to go over this. If the two molecules here are far enough apart, you can determine it. They become closer together. You start having trouble separating them, and you even closer together, and they're unresolved. But if, for example, you have this GFP that's non-fluorescing, it's off, then you shine 400 nanometer light, just one of them comes on, and as long as it's photostable enough, you can get out a good number of photons. By Fiona, you can determine where it is. Eventually the thing photobleaches, and you're back at the beginning. And you do it again, and in general, you excite some other molecule, you determine its accuracy, and because now you know where both of them, you can get super resolution. Okay? So, how many of you guys have done this experiment? And some fraction of you have, and some haven't. Where the idea is you have a microtubule, which is a long polymer that actually is in a circle, and it's the roadway on which kinesin and also this other molecular motor called dynein walks upon. So so the idea is to actually determine what the width is. Because if you just lay some of this down and you attach a dye to this what is called the tubulin dimer, and what if you shine light at it? What width will you think is the width of this?
Lambda over 2.
Lambda over 2, because it's exactly that. And now, so now you want to overcome this, and how are you going to do this? How are you going to overcome? How are you going to get super resolution in this case? And do you have just one dye, or do you have many dyes? What's that? Many dyes. In fact, you have a side 3 here, and a side 3 here, and a side 3 there. Many dyes. Wait, but many dyes, you're starting to go in the ensemble region. Many dyes, it'll be really bright if you shine light at it. And so that's not going to work, right? Because we said, so how are we going to do this? Blinking. Normally, psi 3 is a very good dye. It's a very good dye for regular fluorescence. You somehow have to make them blink. In fact, you somehow have to actually wipe out the fluorescence. And then it has to be in some temporary dark state, and then you have to make it come back on. And in this case, what you do is you add some chemicals to it, then you add like 561 nanometer light, so it's in the green, and you hit it like crazy, and you hit it for like, you know, a minute, and then you see nothing. And then you actually, in this case, I think in this case, you shine 400 nanometer light. That will cause some number of the molecules to come back on. And you see here and here, they're clearly well separated. Well, here, you know, it's not so good. So how do you overcome this problem, right? I mean, you know, my guess is, you know, here's one and here's another and here's another and whatever. How do you deal with this problem?
Turn them off and then turn them on again.
Yes?
Lots of pictures.
Yeah. Or let's say you turn them off and turn them on again. But, okay, in the next time, you may get a single one, and so you do that. What's another way? What's, you know, this is clearly a pain, right? Because over here, you're not getting the resolution that you really want to, because you've turned 2 or 3 of them on. So,
You let it go for a while, and some of them will start turning off.
somebody else. Exactly. You decrease the intensity, which? Is this the 561 nanometer or the 400 nanometer? The 400 nanometer. Because evidently, you're hitting it at 400 nanometers enough that, you know, both of them are coming on. So you just decrease it. And eventually, you'll see just one of them. Okay, last thing. I'm sure that's a lie. But this is kind of lousy in that, you know, you had a dye here and a dye here that's both on. So when are we going to say that, you know, we're going to turn our 400 nanometer light down? And when are we going to say, oh, okay, that looks good? Right? So, okay, why don't you get together and talk about this and give me the answer.
then you have learning dimensions. I was just like trial and error. Like, I actually have no idea how mathematics. Experimentally, I would just do the same thing you said with the pet coding and stuff like that in our lab. So just get a bunch of these. Yeah. And then not even that, but there you're not even measuring the location of like anything or anything like that. You're just simply out these fluorophores. And then you say, okay, well, this intensity drives it. This intensity doesn't show us anything. And I'll write, I don't know, maybe write lab view or math code, it just goes. Yeah, I was just. So yeah, never mind. We could see like the relationship between light intensity and your energy carrier. And then try to look at the energies that the molecules receive and give off and derive correlations.
No luck. It's okay. Yeah, it's good that I'm asking you to think about it, and you think about it, then you struggle, and then eventually,
So the question is, when do we know we're good enough yet?
Yeah, and that we don't have three of them within a certain undistinguishable. That, well, what is the limit? Like I'm saying, this guy is, and this guy is overlapping. What does that mean?
We cannot see 2 points per functions.
Yes? Good. Okay. So we can't see 2 point spread functions. Why is that?
Because
They're within lambda over 2.
They're within lambda over 2. And we've accidentally excited both of them. And so when we go and we plot this, what will we see? Yeah, that's right. Normally, if it's 1, this is about 250 nanometers, and this looks like a Gaussian. However, if this will be, I don't know, let's say, 350 nanometers. And it'll tell you, well, in fact, you're probably not seeing just one of them. In fact, because it's 2, it'll be in general somewhat higher, and it'll be wider. So what you do is, when you're going to fit these, you have to make sure that it's always on the order, well, that it looks like a single point spread function. That's all. So there's no fancy math involved or anything. Then when you're sure that, well, when you think you see a single point spread function, well, then you turn your light down maybe another factor of 3, and then you're pretty damn sure. Okay? And this is what it is. In fact, here you can pretty much see that each time it's only a single point spread function. Occasionally, 2 of them are emitting at the same time, and in fact, you typically just throw that out the window. You don't use it. Okay?
So with Fiona, let's say we did Fiona on the Y group.
Mm-hmm.
We could determine the center, but the the standard, the deviation would be different than for the other one. And based on that, we would say it's more than one.
Well, yes, the precision would be the number 350 divided by n instead of 250. But really, the fact that the width, pretty much just the width. Although you have to be, it becomes somewhat tricky because the two dye molecules, if they're only like 10 nanometers apart, in fact, you'd still get, okay, maybe 260 nanometers, and you think, that may or may not be two molecules. Although, in general, this will be twice as high as this. So, yeah, that's right. That's right. Okay? And so this is a conventional fluorescence. As we said, this should be about 250 nanometers. And you see clearly by storm or palm, in this case, actually, typically it's called D-storm. I don't know what direct storm, where you knock them all into some non-fluorescent state and then you bring them back. Anyways, so you can see there and there. Okay, and so who has done this experiment? So you went, yeah, okay. Some of you haven't, and you'll hopefully, I guess, this week do this. And if some of you did it and it wasn't that clear or it didn't work out, this is the way it's supposed to work. Okay? Okay. This is looking at only two dimensions. It looks in the X, Y, because, that's what you're doing. However, you would really like to see in 3 dimensions, X, Y, and then Z. The question is, can you get this? And the answer is, yes, you can. In fact, you can get it amazingly easy. And essentially, the standard technique is this. Up top, you have your X, Y, and you have, let's say, a fluorophore. Then you have your objective. The way it normally works, you forget about this cylindrical lens. You have another imaging lens, and it comes down over here. And if it's a single molecule, it'll be about 250 nanometers wide. However, it turns out that if you insert a cylindrical lens, which you can buy no problem, what a cylindrical lens is, in one dimension, in the X direction, as opposed to the Y direction, in one dimension, it doesn't do anything. In the other direction, it's another lens. And so in combination, this lens has a different focal length. And so what actually happens is kind of amazing, that if you move it in Z, what happens is in one direction, basically this smears out. In this dimension, it hasn't changed, but at this dimension, it gets a little bit longer. So you can take the X and Y dimension, and it turns out the more you move it out of your plane, the more the Y dimension will get. Now that's assuming that you moved the Z-axis, in this case, like minus 400 nanometers. Let's say you took the fluorophore and you moved it in the other direction. Then, in fact, what happens, you see the same thing, but the X direction now gets large and the Y direction doesn't change. And so if you take, so the X direction and this is the Y direction. If you take the X direction divided by the Y direction, it turns out that will have a direct relationship to the amount of Z that you've moved this fluorophore. And so once you have this, that's your calibration curve. Then you can take your unknown sample, always exciting it very weakly, such that at any one point or any one time you're only exciting a single molecule. Then you excite that single molecule, you'll detect it through the cylindrical lens, and you'll get a point spread function that will look somewhere like one of these. And then you say, okay, I know the XY. How do we know what XY? For example, let's say we have the XY and then Z is way different. So you get this. So how are we going to get X, Y, and Z from this? Yeah, it's a little bit confusing. Okay, why don't you talk again? So let's say you have an image like this. How do you get what the X, Y, and Z is? Go ahead.
Professor?
Yeah?
When you set like an image like this, do you know one whose value negative 400?
Yes.
Just that single little dot. Just that square?
Well, yes.
Okay.
Just this. It's not a square. It's more of a rectangle.
Yeah, sorry. Yeah, so we would just
How we get to
look
this.
at the velocity and negative 400 value to see what the maximum is in the X.
Well, in some senses, there's a fluorophore. I mean, let's say that this wasn't here. You get a fluorophore, and you get an image that looks like that, right? Okay. So, tell me what X and Y and Z is. That's the question, right?
Smaller, like the X direction, you're supposed to put that forward and that independent of the Y. So you're doing
And using Gaussian method, you wouldn't even have to like focus it in very well to get it.
John's looking very shy.
Well, you know, when you defocus, if you were
You add?
to storm, you have to like draw the line
Okay.
across the magnitude to find the Gaussian, and then say this is like, oh yeah, you're right, you did full with that maximum.
Yeah, well, that's how you can full width,
Did you guys actually, oh, I guess, no, I guess we're not actually expecting you to do this. Yeah.
Like further away the X1 from each other, like when it's perfectly focused, you assume you need a perfect symmetric so your X1 position should be equal.
But the thing about the perfectly symmetric Gaussian, if you're looking at the out of focus image, right, like the one that's not that's like -400, wouldn't the Gaussian still be the same on both sides?
Oh,
it's a bubble.
no, I mean, it's like symmetric data. So like, if you mirror
Oh, okay.
yeah, like a single perfect beat, then your precision or your fold at both the X and Y direction.
And so you always, you just assume that it's perfectly circular, that that's the true shape of it.
Right, because yeah, in focus is a single photon. It should have a Gaussian distribution. And then the further out of focus you are, the more elongated it is pushed to get in a certain direction. So I was saying, as you defocus or what the zooming around your XY precision will change relative to each other. So like in the minus one, your Y is going to be a lot smaller than it's a lot bigger than your other positions because the Gaussian spread out more. So you can use how, like the difference between them to correlate with how far away, like the actual sign.
I guess maybe you need a control spot somewhere around the.
I lost you.
Okay.
What my question was though, have we gotten to the point where we're so precise that like the shape of the fluorophore can
Right, you would just compare it to the 0, 0.
Well, the only thing we're perceiving is the actual photon.
yeah.
So, yeah, an incoming photon, like, is the
Mhm.
first set of
What would you ratio of the Gaussian? I lost like that.
the ratio of the lens.
Each, like, zoom level, so it's say 0 and 400 zoom levels.
Oh.
Full width at max or both.
Okay, there's two questions. There's how do you get the X and Y direction, and how do you get the Z direction, the magnitude of the Z?
One side is long, the other one is short. So, the greater the difference between them, the less focus you are.
Right, exactly. How do you get the XY direction?
In the Z direction from where you are.
And then perfect focus.
Right, so like you use your like perfect focus as like a reference point to hold what happens, so how it changes with
And in what sense?
incoming focus.
Yeah.
Yeah, I think that works.
Good job.
The pixel.
No, that's
But it's not the same in the X and the Y direction. Okay, why don't we all come together, because
Is that way then things are different, there's a distortion as you change?
okay, so I'm kind of tired of talking, so who wants to lead you through it? You know, you don't, in fact, it's better if you don't know the answer.
Do I have to get up or can I stay here?
You have to get up.
Alright, so the first thing I assumed is that you have your in-plane focus as a reference. So you're trying to determine the distance between two planes of focus of the fluorophore. So for the 0, and we're just using -400 as our two images, you should be able to generate a Gaussian for both the x and the y direction, and they should be fairly independent of each other. So from the two Gaussians you get from both the 0 and -400, you can determine a full width at half max for the x and y directions independently. For the in focus, so the 0 image, your full width at half maximum should be equal because it's a single photon coming in. It should have a symmetric point spread function. But as you
do you agree? Yeah, it's sort of, exactly. At 0, right? There's essentially no distortion, and so the full width half max, you fit it to a 2D Gaussian, you get certain uncertainty in x, certain uncertainty in y, and it should be on the order of 250 nanometers, and you know a certain that you've collected a certain number of photons, let's say 10,000. So you know the x to 10,000 divided by, or 250 divided by 10,000, or square root of 10,000. And similar, you know the y, right? That's where everything is symmetric, right? Okay. Okay, go ahead.
So then as you defocus, or just change your plane of focus, the image you receive will be elongated in one direction and shrunk in the other. So for the 400, if you were again to take a Gaussian for the x and y directions independently, the y Gaussian would be much thicker, and so it would have a smaller precision and a larger full width at half max, whereas the x direction would be smaller by comparison. So from here, I'm kind of uncertain, but I think you can use just how your level of precision as measured from the in-focus plane as a point of reference. You can use the changes in the full width at half maximum to generate the change in the z based on the changes in the full width at half maximums.
Okay, that's very, very close. So how are you going to figure out the extra, let's not worry about the z direction. How are you going to figure out the x direction and the y direction when you have this asymmetric? So can you say it again?
So you can again do it independently just by projecting one Gaussian this way and the other Gaussian that way. So this time it won't.
So draw it out. X versus y versus z. Where z is the photon number.
Okay, so here's your x Gaussian, your y Gaussian, and here's z, or your photon number.
Mm-hmm.
So your x in this case will be pretty narrow. It might be the same as the 0 plane.
Okay.
You have your full width at max. And then the y, by comparison, is a lot more spread out. So you have a much larger full width at maximum. And then this should be taller than the y counts, just because it's more spread out, but you're going to assume it's the same number of counts coming out for each direction.
So how well, and what is x and what is y?
So the x Gaussian, so this is just the x and the y projections, respectively. So is this the projection in the x direction? The axes would, that's intensity. This would just be like bins or channel number, and you can convert that into just meters or nanometers.
So these are basically cross sections of a three-dimensional heat.
Right.
Oh, what I don't get is if you're taking one cross-section one way and another cross-section the other way, isn't the peak height at the same place, so why would they have different heights?
Yeah, that's one thing I'm uncertain about. My logic was that it's the same number of counts in both cases. So the same number of photons you're seeing, like the number of photons you see in this direction is equal to the number of photons you see in this direction, but the y direction is much more spread out, so it can't have the same height.
But what?
And that's just my reason. I could be wrong.
You can have a broader base though and still have the same height, right?
So, or let's say this is the y-axis, and in fact, the x-axis is along here, and it has a certain delta x, and it has a certain delta y, and in fact, this is one peak. So this is what? It's wrong. Okay? Because exactly, it's a single peak, and it's just that the mountain is really wide in one direction, and it's fairly narrow in the other direction. Okay? And so what do you say is the xy of this thing? Or
So
you can
projections of the
good.
image.
Okay.
Right,
And,
so this is the x projection, the y projection of
good.
the 3D Gaussian.
Okay. And where's the peak?
Same point.
Oh.
Let's call 0 and it'll be the same height.
Okay. And so the x direction, let's say the x direction hasn't changed at all because it's going through a cylindrical lens, but cylindrical lens mean in one direction it doesn't change and the other direction it does. So the uncertainty in your x direction is always, remember, this width divided by the square root of n. So it's unchanged. It's 250 nanometers divided by the total number of photons. Okay? Now, what about the y direction? What's the uncertainty in the y direction?
Much larger than it initially was.
Okay.
Its width is larger, so
Yeah.
width over root n is a larger fraction.
That's right. You know, it looks like roughly in that 400 nanometer, minus 400 nanometer, it's roughly, 2 or 3 times the width. So the width is, instead of 250, it's, 500 or 750 divided by the square root of n. So, and that's right. So you have actually lost a little something. So now we have the x and the y. We've done it. Okay. Now I want to get z. How do we get z? Say it again. The intersect. I'm still,
The width or the width in the y direction and the width in the x direction of the people.
That would be when it's in plane of focus, I think, is when that's in the calibration curve.
Oh,
0 is when it's
I
in plane
see.
of focus, so then you can calculate the ratio of the,
here they're equal, but we said we have this, although, we don't have this for right now. We're trying to figure out what that is. So what do you do? Yeah, Melanie?
I think we have the calibration curve already, so having found the widths of the x and y, you should be able to calculate that ratio and find it from the calibration curve.
That's exactly right. You've independently, you've made this calibration curve, and that, for example, you look where it's exactly in focus at 0. And then what you do is you move your microscope, you move the fluorophore such that you're 200 nanometers closer. So that's now a given. And at 200 nanometers, what you find is that, the ratio of y to x is, I don't know, about 2. Then you keep going. You do 300 nanometers, you do 400 nanometers, and you find, okay, that ratio is about 4 to 1. I'm making things up. Okay, and so then you go and look at, you have this, and now you want to go and look at your real sample, and you find that, okay, you get x and y, and you take the ratio of the x, the uncertainty in the x, the uncertainty in the y, and then you go back and you look. Okay, it's corresponding to this. It must be at 300 nanometers. So now you've got an x, y, and z. And it's perfect. It's sort of amazing. And then, so you've done this for one point, now you've got an x, y, and z, and then you do it for another point. And again, you have to be careful, because you only want to excite a single one here, and then you do a single one here, and then you do a single one here. So it can take you quite a while. And that's the way it is. Initially, in terms of just, as I said before, the very first measurement took, only looking at x and y, took 24 hours. Nowadays, you can do it in maybe a few minutes' time, but 30 minutes is actually quite common. Okay, thank you.
But the calibration curve for Z is not linear, right? It's not.
Yeah, maybe. In general, I think it is nonlinear, but it's whatever it is that when you move a microscope or you move a fluorophore 200 nanometers and then 300 nanometers, it's whatever it is.
Another question about the Z, when we were talking about the Gaussian, you said, and the width change, the width increase, from the significant ends. Did the end change as well?
What do you think?
It didn't.
What?
The point was very small, does it change?
What do you think? Doesn't change? You're hitting it, you're collecting all of the light, and you're collecting it on the EMCCD. Now, this is truly my last point, that over here, it may be you can fit this to 8 by 8, and so you have a certain amount of dark noise due to the EMCCD. So in this case, it's like 8, but in fact, it may be over like 32 nanometers or so, or 30 nanometers or so forth. So to the extent that this is not, really strong, that you have the background due to the EMCCD is actually significant. The precision of which you can determine this is actually slightly less here than here. But that's that's a minor point. Okay, thanks a lot, guys.